Hello everyone, welcome to this part 3 of this of reading this blog on Google research, which is about teaching AI to read map. In part 1 we discussed like what this paper proposed. Like this paper was proposing synthetic data generation to train AI systems to visually follow any route on any map. So basically the reason this was this they, they worked on this problem was that the LLMs, like humans, have this spatial reasoning knowledge inbuilt, which using which we can identify, we can read at a blog and then find faults, like analyze it and then trace a route from point A to point B. This is our brain is has this quality inbuilt. But how do we transform this in a large language model? So large language models basically have a difficult time tracing a valid path from entrance to the destination. Here they have given the image of a zoo, and then they asked the LLM to trace the route, which it was finding it difficult to do that tracing of the route. Uh, it would basically draw a straight line, uh, but then it failed to respect the basic constraints of the map. They call it 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 doesn't it failed to understand the geometric and topological relationship between the objects. Now, to address this challenge in map trace, um, this paper they introduced a task a new task dataset and synthetic data generation pipeline designed to teach multimodal LLMs to the fundamental skill of tracing path on map. Now, uh, this shows the path from point A to point B on the provided path. I will rush through part 1 and part 2, which I already did in the part 1 part 2 videos. You can go there and see. I will just um, jump to the solution part that that was pending for part 3. So here basically this pipeline proposed like 4 stages. First is to generate a diverse map. So you give a prompt and then it generates images of the map, multiple image generator. Given a prompt, it generates images. Second is you have a another LLM. Once you have the image map, you identify the walkable areas. Our system does this by clustering the pixels by color to create candidate path mask, essentially black and white maps of all the walkways. So it generates path mask, black and white images, um, by doing the by clustering the pixels by color. But not every shaded region is a valid path. So we employ another multimodal LLM as a mask critic, used to examine each candidate mask and judge whether it represents a realistic connected network of path by looking at both the map image and the mask candidate. So, um, so basically they employed another multimodal LLM. So first LLM was to generate image by giving a text description, okay, image of map. Second is another LLM which is called a critic. What kind of a critic? Mask critic. So the system generates multiple path masks by clustering pixels by color, and then they employ a LLM called mask critic to judge whether it represents a realistic connected network of path. Okay. Third is uh, with a clean mask of all areas, traversable areas, we convert the 2D image into a more graph format, building a navigable graph. Think of this as creating a digital version of the road network. So once step 1 is you generate multiple images using a prompt using the first LLM. Second, you do mask, you could generate path mask by clustering the pixels by color. Third, like in this step itself, you employ LLM another LLM as mask critic, which examines each candidate mask and then judge whether it represents a realistic connected network of path. Third is, and then the high quality masks are passed to the next stage. Third is, with this clean mask of all traversable areas, we convert the 2D image into a more structured graph format. Think of this as creating a digital version of the network where intersections are nodes and the road between them are edges. You create a graph out of these 2D valid masks, clean masks, um, and then this pixel graph captures the connectivity of the map, making it easy to calculate the routes computationally. So once you have a graph representation of a 2D image, you can apply any algorithms which work on graph, and then gives you a better ability to calculate route from one node to another. That is step 3, building a graph. Step 4 is employing a path critic. Now we have thousands of random start and end points on the graph on each map, and then we apply Dijkstra algorithm to find the absolute short path between these points. Then we use another, this is like third LLM, multimodal LLM, called path critic, to perform the final quality check. This critic looks at the finally generated path overlaid on the map image and gives it a thumbs up or thumbs down, ensuring the route is logical, stays within the lines, and looks like a path a human would take. So yeah, these are the 4 stages they have proposed, and then basically created a pipeline that does that. Now coming to the last section of this blog, which is the results. What did they found? The results: a clear path to better spatial reasoning. Now the whole point of this project was to inject the understanding of spatial understanding in a LLM, which humans have and by default LLMs do not have. um, how do they find road network, or how do they find route on a map, or basically read a map properly? How do we train AI? So does training on this synthetic data actually work? To find out, we fine-tuned several multimodal LLMs on smaller subset of generated data, 23,000 path taken from our dataset, including the open Gemma 327 billion parameters and Gemini 2.5 flash. We then evaluated their performance on Map Bench, a popular benchmark composed of real world maps with multimodal LLM that had not seen during the training. So they did this benchmarking using this Map Bench performance benchmark. Now we measured the model's path performance error using the normalized dynamic time wrapping metrics. So this is another metric called NDTW, normalized dynamic time wrapping metric, which is an extension of dynamic time wrapping, used to compare two sequences of coordinates that can vary in speed. Now the output is then normalized by the total path length to obtain the final normalized metric, that is the distance between two paths with a lower value, demonstrating better performance. The figure below shows how the NDTW metric is computed, detailing the alignment process. Okay, this is too much for me to understand. Looks like I need to have that understanding of statistics and whatnot. But the overall I can see is 2D path alignment. This is the query path, this is the reference path. Okay, accumulated cost metric, optimal path. Okay, pairwise distance matrix, coordinated comparison. Now fine-tuning on our dataset substantially improved the model's ability across the board. The fine-tuned Gemini 2.5 Flash model, for example, saw its NDTW drop significantly, achieving the best overall performance. More importantly, the models became far more reliable. The success rate, okay, okay, fine-tuning on our dataset substantially improved the model's ability across the board. The fine-tuned Gemini 2.5 Flash model, for example, saw its NDTW drop significantly from 1.29 to 0.87, achieving the best overall performance. Now NDTW is this normalized dynamic time wrapping metric. Okay, Now, more importantly, the models became far more reliable. The success rate, the percentage of time the model produced a valid parsable path rose for all models. The fine-tuned Gemma model saw 6.4 point increase in its success rate and improved NDTW, a dramatic improvement that demonstrates a newfound robustness. This means that after training on our dataset, the model weren't just more accurate, when they succeeded, they were far less likely to fail completely. Okay, average NDTW improvement, pre-trained, fine-tuned. This is this has gone down, NDTW metric, and then success rate improvement. This has gone up for both the models using MapBench performance benchmark. This gain confirms our centralized hypothesis. Fine grained spatial reasoning is not an innate property of multimodal LLMs but an acquired skill. So, what is acquired skill here? So, basically, we have converted a 2D image of a net of a so normally LLMs produce images. We have found we have masked that image, and then by color, like the pixel mapping, let me see what it was. Yeah, this one. By clustering the pixels by color, they have created masks, path masks. Out of these, they have employed another LLM to call mask critic to come up with better high quality masks. Then they converted this 2D image of high quality masks into, these are masks, into, this is high quality and this is high quality, into, we have converted this into proper graph format. Once you have a graph format, you basically can apply pathfinding algorithms on top of it. So now imagine this is like, one is you have a 2D image and then you ask LLM to look into it and then find path. Another is you make LLM more skilled by giving this extra layer where it converts 2D masked path images into graphs, on top of which you can apply any path algorithm like Dijkstra algorithm, and then do the, so basically you have injected spatial reasoning ability to the LLM. So it says these gains confirm our centralized hypothesis. Fine-grained spatial reasoning is not an innate property of multimodal LLMs but an acquired skill. So this is to be acquired. With the right kind of explicit supervision, even if it's synthetically generated, we can teach models to understand and navigate spatial layouts. So now this I can understand is, we can implement this in a lot of use cases. One is you can have a vision camera which is part of a robot which can analyze your room or a place and then take judgments about depth. You can employ it in, say, autonomous vehicles, which is actually looking at a map and then taking decisions on the route that it has to follow, because now it's not just an image, it's a graph that it is looking at. Now, evaluating the performance of AI critics. Okay, for the path critic, we manually reviewed 120 decisions across 56 randomly sampled maps, achieving 76% accuracy with an 8% false positive rate. Misclassifying background regions as traversable when colors resemble paths, and missing thin valid path within larger open regions. For the mask critics, we inspected 200 judgments over 20 paths, observing 83% accuracy and 9% false positive rate. Common errors include background pixels included due to color similarity, small non-path elements. Okay, I don't understand this part, but I feel that understanding this much is a good level of understanding this blog post and understanding how we can inject an acquired skill of making an LLM understand or read a map by converting that 2D image of a map into a graph. I hope this was useful. Thank you very much.